So this is T Kushi from ITA, and my topic in Maths for Tech Talk is matrix method for principal normal form of proportional formula. So first, before going to that, let us know generally how to find the rank of the matrix using normal form. So for finding the rank of the matrix using normal form, you have to convert the matrix into either of four forms, that is IR00 or IR0 or IR0 or IR. So the matrix of the forms of these four forms are known as normal forms or canonical forms, where IR is the identity matrix of order R. Here we have to note a point that the rank of the above normal form is order of the identity matrix. So let us look at the example. So example to find the rank of the matrix. So here we have taken a 4 by 4 matrix. So the method which we follow is that first row, first element should be non-zero. So below elements of that will be made as 0 using row transformations. So if you see in the given matrix, the first row, first element is 0. So we are exchanging row 1 with row 2 to satisfy our condition. After that, according to our condition, first row, first element should be non-zero and below elements will make 0 using row transformations. So row transformations are row 3 changes to row 3 minus 3 row 1, row 4 changes to row 4 minus row 1. So after that transformation, you will get a matrix. Now the second step is that first column, first element should be non-zero, and next beside elements will be made as 0 by using column transformations. So here column transformations are column 3 changes to column 3 minus column 1, column 4 changes to column 4 minus column 1. So after this transformations, you can see you will get a 4 by 4 matrix again. So next step, after this, the next step is that second row, second element should be non-zero and below elements will make it as 0 by using row transformation. So row transformations are row 3 changes to row 3 minus row 2, row 4 changes to row 4 minus row 2. So after the transformation, you will again get a matrix, 4 by 4 matrix, and then the next step is in the same way as we did for rows, we'll do it for columns. So second row, second column, second element should be non-zero and the beside elements will be maken as 0. So column 3 changes to column 3 plus 3 column 2 and column 4 changes to column 4 plus column 2. After this column transformations, you will get a matrix which can be written in the form of I2 0 0. So from this we will know the rank of the matrix is 2, because rank of the matrix is nothing but the rank of identity matrix, or order of identity matrix is nothing but the rank of the matrix. So here identity matrix order is 2. So rank of the matrix will also be 2. We'll go with another example. Here also we are considering a 4 by 4 row transformations. So what is the first method? First row, first element should be non-zero. We are making below elements 0. And in the same way, first column, first element should be non-zero. We are making the beside column elements as 0. So let us see the row and column transformations. Row 2 changes to row 2 minus 2 row 1. Row 3 changes to 2 row 3 minus row 1. Row 4 changes to 2 row 4 minus row 1, and column 2 changes to column 2 plus column 1, and column 4 changes to column 4 minus 3 column 1. So after this all rows transformations and columns transformations, will get a matrix. Again we are going to get a 4 by 4 matrix. So after getting this 4 by 4 matrix, the next step is second row, second element should be non-zero. Below elements will make it as 0 by using row transformations. So as we can see already, third row element is 0. So we'll directly make fourth row element as 0. That is row 4 changes to 3 row 4 minus row 2. After this, again we are going to make the column row 0. So second element of the second column should be non-zero. Beside elements will make it as 0 using column transformations. So column transformation is 6 column 4 plus 10 column 2. Then you will get again a 4 by 4 matrix. Here we are going to exchange row 4 and row 3. After exchanging, we are obtaining again a 4 by 4 matrix. Here next we are going to use the transformation. Third row, third column, third element should be non-zero. So yeah, third column, third element should be non-zero. Beside element we are making as 0 using column transformation. So column 4 changes to 6 column 4 plus 96 column 3. After this column transformation, you are again going to get a matrix. So here after obtaining the 4 by 4 matrix, you are going to divide row 1 with 2, row 2 with 6 and row 3 also with 6. After this again you are going to get a 4 by 4 matrix which can be written in the form of an identity matrix. So it can be written in the form of I3 0 0 0. So here rank of the matrix is nothing but the order of the identity matrix. So order of the identity matrix is 3, that is I3. So it is 3. So therefore rank of the matrix will also be I3. Next, coming to DNF, disjunctive normal forms. A formula which is equivalent to a given formula and which consists of a sum of elementary products is called as a disjunctive normal form of a given formula. So you can see the example as P and negation Q, or Q and R, or negation P and Q and negation R. The DNF of formula is not unique. So if you use this DNF method to find the normal form, then you will not get unique values. So that is one disadvantage of this DNF. Next, coming to CNF, conjunctive normal form. A formula which is equivalent to a given formula and which consists of a product of elementary products is called a conjunctive normal form of a given formula. Example, P negation or Q and Q or R and negation P or Q or negation R. The CNF of formula is not unique. Same as DNF, here also the CNF of formula is not unique. That means you will not get unique values. If every elementary sum in CNF is tautology, then given formula is also a tautology. So in reason for using principal normal forms, generally you can use the DNF or CNF methods to form normal forms, but we particularly use principal normal forms because in DNF and CNF you will not get unique values. So to get unique values, you are going to use this principal normal forms. So the DNF and CNF of a statement formula is not unique. In order to obtain unique result of a given statement formula, we introduce principal normal forms. There are two types of principal normal forms: PDNF, that is principal disjunctive normal form, and PCNF, that is principal conjunctive normal form. So principal disjunctive normal form. An equivalent formula consisting of disjunctions of min terms only is called the principal disjunctive, and it is also called as sum of products of conical form. So you can see the example given below. The min term consists of conjunctions in which each statement variable or its negation but not both appears only once. The min terms are written down by including the variable if its truth table value is true and its negation if its truth value is false. Normal form of the formula. So methods to obtain PDNF of a given formula. So there are two methods to obtain PDNF values. One is by using truth table and other is without using the truth table. So first let us see by using the truth table. For every truth table T of the given formula, select the min term which also has the truth value T for same combination of truth values of statement variables. So as you can see in the first picture, we are going to write the truth table for P conditional Q. So P conditional Q consists of two variables. So P conditional Q and min term. So if P and T are true, then P conditional Q will also be true. If P is true and Q is false, then P conditional Q will be false. If P is false and Q is true, then P conditional Q is true. And if P is false and Q is false, P conditional Q is true. So if you observe P conditional Q is only false when P is true and Q is false. So while writing PDNF, we are not going to consider this condition. That is, when P is true and Q is false, this condition is not going to be considered. So now let us write the min terms of rest all conditions. So for P is true and Q is true, the min term is P and Q. And for P is false and Q is true, the min term is negation P and Q. And for P is false and Q is false, the min term is negation P and negation Q. So in the next slide, you can see that these min terms are connected or are connected with each other with the help of R connectivity. So you can see that first one, negation P, negation Q, or negation P and negation Q, or P and Q. This is the PDNF value of P conditional Q. If you are taking three variables, then you will get the condition as P and Q and R, or P and Q and negation R, or negation P and Q and R, or negation P and negation Q and R. So this is an example for truth table. Using truth table, how to find the PDNF value, and we found the PDNF value for P conditional Q. Now without using truth table, to find the PDNF value, we have to follow certain steps. So we'll see the steps first. PDNF without using truth table. Replace the conditional and biconditional connectivities in the given statement formula by their equivalent formulas containing only and, or, and negations. Apply negations to the variables by using De Morgan's law followed by distributive law. Any elementary product which is a contraction is dropped. Min terms are obtained in the disjunction by introducing missing factors through the complement law and then apply the distributive law. Identical min terms appear in the disjunctions are to be deleted. So let us look at one example so that you can understand how to find the PDNF value using truth table, or I mean using without truth table. Obtain the PDNF of P conditional Q. So the given statement is P conditional Q. So this can be written as, so conditional is replaced by biconditional way. So P conditional Q is written as negation P or Q. So negation P or Q is further written as, negation P is written as negation P and T, or Q and T. So here we are writing negation P as negation P and T because negation P and T are technically equal to negation P, and Q and T are technically equal to Q. So we are writing it in that way. And in the next step, we are writing it as negation P and Q, or negation Q, or Q and P or negation P. Here we are replacing the T variable with Q or negation Q and P or negation P because these both are technically equal to T. So in the fourth step, we are applying distributive law and writing the equation. So the equation after applying distribution law will be as negation P or Q, or negation P and negation Q, or Q and P, or Q and negation P. So after applying the distributive law, you will get it in this way. Here we are going to eliminate the similar terms, that means same terms. In the next step, if any terms are identical or same, we are going to write them as 1. So if you see in the next step, that is in the fifth step, we are having negation P and Q, or negation P and Q, or negation P and negation Q, or P and Q. So as you can see, negation P and Q we have 2 times. So by using the formula, that is P and P is equal to P, so we'll write it only 1 time. So in the next step, that is in the sixth step, we'll get it as negation P and Q, or negation P and negation Q, or P and Q. So this is the required PDNF of P conditional Q, that is negation P and Q, or negation P and negation Q, or P and Q is the PDNF value of P conditional Q. Next we are going to see PCNF, that is definition of PCNF. For a given formula, an equivalent formula consisting of conjunctions of the max terms only is known as its principal conjunctive normal form. PCNF is also called as the product of sums conical form. So here also, in the same way as PDNF, you will have two methods, that is using truth table or without using the truth table. So first we'll see using truth table. For every truth value false of the given formula, select the max term which also has the truth value false for same combination of negation of truth values of statement variables. So let us look at the example. So here we are going to find the PCNF value of P biconditional Q. So given formula is P biconditional Q. Number of variables in the given formula is 2. N value is 2. So number of rows in the truth table is 2 power n, that is 2 square, that is 4. We will get 4 rows. So if you see in the table, first row is P, second row is Q, third row is P biconditional Q, and the fourth row is max terms. So if P is true and Q is true, P biconditional Q is true. If P is true and Q is false, P biconditional Q is false. If P is false and Q is true, then P biconditional Q is false. If P is false and Q is false, P biconditional Q is true. So in PCNF, we are only going to consider false values. That is, when P conditional Q is false, only those conditions are to be considered and those max terms are to be written. So second and third conditions are to be considered. So for that, for second condition, the max term will be negation P or Q, and for third condition, the max term will be P or negation Q. So therefore, the equivalent PCNF of P biconditional Q is negation P or Q and P or negation Q. So the second method is without using truth table. Replace the conditionals and biconditional connectivities in the given formula by OR connective, AND connective, and negation connectives. Apply negation to the variables by using De Morgan's law followed by distributive law. Any elementary sum which is a tautology is dropped. Max terms are obtained in the conjunction by introducing missing factors. Identical max terms appearing in the conjunctions are to be deleted. So let us look at one example. So here we are going to obtain the PCNF value of P biconditional Q. So given formula is P biconditional Q. Here P biconditional Q, biconditional is replaced by conditional line. So it can be written as P conditional Q and Q conditional P. Since P biconditional Q is equal to P conditional Q and Q conditional P. In the next step, we are going to write it as negation P or Q and negation Q or P, because P conditional Q is technically equal to negation P or Q, and Q conditional P is technically equal to negation Q or P. So after this, we are going to get it as negation P or Q and P or negation Q. So the required PCNF of P biconditional Q is negation P or Q and P or negation Q. Thank you. I hope you understood this. Thank you so much.